All right, so we just finished this example where we used conservation of energy to figure out the speed of the car. So now we're going to talk about energy diagrams. So you've probably noticed if you've read the book that the author really likes diagrams, energy diagrams. So this, believe it or not, is free fall. So you're just dropping something. So remember, for free fall, the gravitational potential energy is mgh. Or if you want, you can say mgy. So if we're going to make a graph of ug versus y, well, this is a straight line, right? This is a straight line where this is the slope. So we just get a straight line. All right. So that's what we have here. So this is energy. It's not just potential energy, it's also kinetic, right? So this is energy, kinetic plus potential. And this is the height, or the y. And again, this is just ug mgy. And it kind of makes sense, right? Because right at this, when we're just holding it steady, the kinetic energy is 0, so the total energy, E, is the potential energy. And then when we let go, the potential energy gets smaller and smaller and smaller and smaller and smaller until it just stops. I mean, until it hits the ground. All right, now, here's the question. So again, this is total energy. This is potential energy. So how do you find kinetic energy? Well, hopefully, this is the kinetic energy, right? Because again, potential energy plus kinetic energy equals total energy. And think of it physically. Initially, all it has, when you're holding it, all it has is potential energy, no kinetic. Then you drop it, the kinetic energy gets larger and larger, potential energy gets smaller and smaller. When it hits the ground, it's all kinetic, no potential. So there you go. So again, you can see, right, we're ignoring friction, and so this is conserved. So everywhere, kinetic plus potential is the constant energy. Kinetic plus potential is the constant energy. So that's one way to look at it. Here's another way to look at it. So here's a situation where we're shooting a ball up. So it's free fall, right? It's still free fall. So here's that plot again. Now this is from a different book. So TE means total energy, PE means potential energy. So there's that potential energy line, just like before. But instead of dropping it, like I talked about, this time we're throwing it up, and we're starting at y equals 0. So initially, the potential energy is 0, right? Because it's at y equals 0. So it's all kinetic. So it's all kinetic, no potential. Then we get, maybe halfway up or something like that. And so we're at some YB. So this is the potential energy, and this is the kinetic energy. So it looks like they're half and half, right? Almost the same. So here, that's the kinetic energy, that's the potential energy. And again, the potential energy plus the kinetic energy equals the total energy. All right, then we get to the turning point, and remember that's when the ball stops. So that's the turning point. So since it stops, there's no kinetic energy. So it's no kinetic energy, all potential energy. And that's here, right? Because this is all potential energy, which is equal to the total energy, no kinetic energy. Then it goes back down, and so the potential energy, this is the potential energy, it decreases, there's the kinetic. Again here, there's the potential, there's the kinetic. So you should be familiar with this kind of energy graph as well as this kind of energy graph. You should be able to interpret them and basically figure out what's physically going on. Okay, so that's for free fall. Let's do something else. And we're going to be talking about this later. That's why we're talking about it now. We're going to also be talking about it in Physics 106. So this is spring potential energy. So just imagine you have a spring attached to a wall, and if you just leave it alone, it's going to extend out to 0. So we call that the equilibrium length. Right? You just leave it alone. You don't touch it. But if you pull it, you can pull it all the way to x equals a, or you can compress it to x equals minus a. If you ignore friction, if you pull it out here and let go, it's just going to go back and forth, back and forth, back and forth. Right? So that's what we mean. So x equals 0 is the equilibrium length. Okay. Now, the potential energy for a spring is this. So the potential energy for a spring is 1/2 kx squared. I said this before, but k has to do with how stiff the spring is. And again, x is the distance from the equilibrium, from the 0 point, either this way or that way. All right, so hopefully a long time ago you learned that this is just a parabola. All right, that's just a parabola. So there it is. So again, this is the energy, and this is the x. And so here's our 1/2 kx squared. And when let's say we're going to pull it. Let's say we pull it here. And then, so we're holding it. So we pull it and we just hold it there. So it has no kinetic energy, but it has maximum potential energy. The same thing would happen if we compress it, right, to this point and hold it. No kinetic, all potential. So you see here at x equals a, the total energy, k plus u, is just potential. Just like here, it's all potential. But when you pull it here and you let go, the potential energy is going to get smaller and smaller, and the kinetic energy is going to get larger and larger. Now right here, at the equilibrium length, x is 0, so the potential energy is 0, so it's all kinetic energy. And again, you can see that, right? So here's the potential energy, gets smaller and smaller and smaller as you go this way. Kinetic energy gets larger and larger, then it gets smaller and smaller, and stops. Okay, so again, if this is the potential energy, this is the total energy, then this is the kinetic energy. So it's 0 at A and negative A, and it's maximum, right? The kinetic energy is maximum right here because there's no potential energy. Now, you can plot that a different way if you want. So that's what you do here. So the blue is the potential energy, 1/2 kx squared. And the green is the kinetic energy. So it starts out at 0, gets larger, 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 maximum, right? 0, larger, 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 maximum. Then it gets smaller, smaller, smaller to 0. So you can do that. So again, you should be able to understand these graphs. Okay. Now, here's another way of looking at the spring. All right? So again, this is the equilibrium length, xe or 0, whatever you want to call it. So what you're going to do is you're going to pull it to here and hold it and then let go. When you let go, it's going to go back and forth, back and forth. So that's what this is supposed to show you, right? Back and forth, right? Okay. All right. So here, you're holding it, so the potential energy is maximum, kinetic energy is 0. Here you go, right? Kinetic energy is 0, potential energy is max. Now you've let go, so the potential energy gets smaller right here, but it's going faster, so that's kinetic energy. So there's kinetic, there's potential. And again, if you were to stack this on top of this, it'd be the same as this, right? Because the energy is constant, right? So this here equals that plus that. Okay, now we're here at the equilibrium length. Well, there's no potential energy, right? Potential energy is this. equilibrium length is x equals 0, so it's no potential energy, because it's not stretched, it's not compressed, right? It's just happy, you know what I mean? Okay, so it's all kinetic energy, all kinetic energy. So potential energy is 0, this is all kinetic. This is what this says. Kinetic energy is max, no potential. So this is the same height as this. And then we go past this, now we can start compressing the spring, so the potential energy increases and the thing slows down. So here's the potential energy, this is the kinetic energy. Okay, on the bar graph, there's the potential energy, there's the kinetic. If you put this on top of this, it should be the same height as that. So make sure you understand these graphs, not just for this chapter, but for the future. All right, this is what I'm going to call this a generalized energy diagram. What does that mean? It means I don't know what it's supposed to represent. I don't even care. We're just going to learn something from it, right? So this may not stand for anything physical. I don't care. We're just going to learn something from it. All right, so so again, this is the potential energy, right? So this is the potential energy. Okay, all right. Now, but we don't have the total energy drawn yet, so we can't figure out the kinetic energy. So there you go. So this is the total energy, 1.5 joules. And let's say that this object is moving in this direction, all right? So this is the kinetic energy, right? So where does the object speed up? Well, that means that the kinetic energy is increasing. Well, here the kinetic energy is 0, but here it's getting larger and larger and larger. So from x equals, I don't know, 0.7 or something like that, to x equals 1, the kinetic energy is increasing, so the particle is getting faster and faster. Here, the kinetic energy is decreasing, so it's going slower. Here, the kinetic energy is increasing, so it's going faster. So from like 2 to 3, the kinetic energy is increasing, so it's going faster. Here, the kinetic energy is decreasing, so it's going slower. So like from x equals 3 to x equals, I don't know, 3.6 or something, it's going slower. Okay, where is the speed the greatest? Where's the kinetic energy the greatest? Well, where there's no potential energy, right? So here there's no potential energy, so the kinetic energy is maximum. Here there's no potential energy, so the kinetic energy is maximum. Okay, where's a turning point? So the turning point is where the speed is 0 and the direction changes. So this is a turning point at x equals like 0.6 something. This is a turning point, x equals 3.6 or something like that. Okay, now let's talk about over here and over here. So, let me write down. So I'm just going to say this is x equals 0.6 or 0.7 or something like that. So let's look at x is less than 0.7 meters. Now, this is called forbidden, okay? It's forbidden. The particle may not be there. What do you mean, may not be there? Why not? Well, look, if you're x less than 0.7 or so, the potential energy is bigger than the total energy, right? You know, so in this region, the potential energy is greater than the potential energy is greater than the total energy. Well, wait a second. The total energy is U plus K, correct? So how could U be bigger than U plus K? The only way that's possible is if K is negative. Now remember, kinetic energy is 1/2 mv squared. How can that be negative? You can't have negative mass, so this is impossible, so that's impossible, so the particle cannot go over here, okay? Because you'd have to have negative kinetic energy. Same argument over here. The particle can't be over here because the potential energy is greater than the total, which would mean that the kinetic energy is negative. All right? So this is called this is called forbidden, and this is called forbidden. All right, that's all. Now, what energy transformations are occurring? It's just potential energy is going to kinetic energy, that's all. So it's just a transformation that we've seen before between potential energy and kinetic energy. All right. Let's consider this now. So now we're saying that the total energy is a half a joule, right? So the total energy is a half a joule. Now what we want to do, we want to just say that the particle is right here at x equals 1 meter. And what we want to do, we just want to disturb it, maybe blow on it or give it a little flick, just disturb it a little bit, right? Just a little bit. Now, as a particle moves away, let's say this way, as the particle moves away this way, what happens to the kinetic energy? Well, again, this is the potential energy. This is the kinetic energy. So if we just move it a little bit to the right, the kinetic energy gets smaller and smaller and smaller, right? Okay, now, what's going to happen to the potential energy? It's going to the right. It's going to get larger. So the potential energy is increasing, right? And the kinetic energy is decreasing. Now, this is going to go all the way up to here, where the kinetic energy is 0 and the potential energy is max, right? Then what it's going to do, then it's going to go the other way. All right, so here, kinetic energy is increasing. Then it gets to here, kinetic energy starts decreasing. And then it goes the other way. So it's just going to go do. All right, that's what's going to happen. So we say that there's going to be small oscillations around x equals 1. It's just going to go and there's a nice analogy for that. So this is actually called a stable equilibrium. Because, again, if you just flick it this way, it's going to go up here, then it's going to stop, and it's going to go down here, then it's going to go... when you flick it, it's going to go this way, then it's going to stop, then it's going to go this way. Stop, this way, Okay. So the nice analogy for that is, here's a bowl. Let's say you put a marble at the bottom, and you just flick it a little tiny bit. What's it going to do? It's just going to go back and forth, back and forth, back and forth, right? So that's called stable equilibrium, right? Where the point, where the object just moves back and forth, all right, around near that x equals 1. Okay, is there another stable equilibrium point? Yeah, right here, right? If the particle were here and you flicked it either this way or that way, I don't care which way you do it, it's just going to go back and forth, back and forth, back and forth, right? Kinetic energy is going to get smaller and smaller, potential energy is going to get larger and larger, it's going to go back and forth, back and forth, back and forth. So that's stable equilibrium, right? Stable equilibrium. Now how about, let's change it. Now let's say that the total energy is a joule. Okay, the total energy is a joule. So now let's say that the particle is right there at x equals 2 meters. So again, we're just going to flick it a little tiny bit or blow on it or something like that. Well, here's what's going to happen. The kinetic energy is going to get larger, 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 larger. Is it ever going to come back here? No, it's never going to come back here. Same thing here, right? Kinetic energy is going to get larger, larger, larger. It's never going to come back here, It's going to get stuck in here maybe or stuck in here, but it's never going to come back here. So what's a nice analogy with that? Well, so this is called unstable equilibrium. So now you have a bowl upside down. You put a marble right at the top. You just balance it perfectly. Then you just blow on it. What's it going to do? It's going to come down or come down. It's never going to go back, right? So that's called unstable equilibrium. We'll use that in the future. That's why I'm kind of going over it now. So anyway. All right, next topic. We want to talk about elastic head-on collisions. Elastic head-on collisions. So let's say you know the mass, you know the initial velocity, you know the mass. This initial velocity is 0. So this thing is just going to smash into that one. All right? And what we want to find this ball's final velocity and this ball's final velocity. That's what we want to do. So how are you going to do that? Well, what's conserved? I mean, it doesn't really spell it out, but there are no external forces, right? There's no mention of gravity or drag or anything like that. So there's no external forces, so it's an isolated system. So therefore, we know that momentum is conserved, which basically says momentum is constant. Now, I said elastic. So these are like, metal spheres or something like that. They don't deform like grapefruits. So if it's elastic, that means that kinetic energy is conserved, or kinetic energy is constant. Okay, so we have two conservation laws. Well, that's cool. So let's write them down. Let's do momentum first. Now everything's along the x direction. That's nice, so I don't have to go crazy with the vectors. All right, so the momentum of this guy is just m1 v1 initial. The momentum of this guy, I know it's 0, but I'm going to write it down anyway, just because. So it's m2 v2 initial. Okay, what's the final momentum? Well, it's going to be m1 v1 final plus m2 v2 final. Okay, now let's do kinetic energy. So 1/2 m1 v1 initial squared. And I know this is 0, but I'm going to write it down anyway. 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Okay, now remember, what we want here is v1 final and v2 final. Well, there it is, there it is, there it is, there it is, right? So two equations, two unknowns. So actually, it's a lot of math. I'm going to skip it, sorry. But if you really want to see how it's done, you can look in the book. So I'm just going to give you the answers. Lazy. Okay, so here's the answers. So v1 final is this expression, and v2 final is that expression. So let's look at it. Let's look at it closely. See if it agrees with your experience. All right. So let's say that m1 is less than m2. So I don't know. Maybe this is like a ping pong ball or something. Well, no, I don't know. Let's say this is a rubber ball. No, it has to be a sphere. It has to be hard. Anyway, who cares? This is less than that, all right? Let's not worry about it, okay? Not tons less, just a little bit less, okay? So this is less than that. So let's see. So have you ever played pool or, I don't know, some kind of game and seen what happens when this is less than that? Well, let's just do the math, okay? If this is less than that, then m1 minus m2 is negative, right? So this will be negative. This will be positive. And we already know this is positive. So that means that v1 final is going to be negative. All right? So that means that if this is less than that, this is going to hit, then it's going to bounce back. And, okay? How about this? It's just going to, I don't care what, if this is less than that, doesn't matter. It's just going to go forward. It kind of makes sense, right? So if this is lighter than that, this is going to go pew, and this one's going to go pew, all right? How about if the masses are the same, all right? So this is pool, billiards, all right? If the masses are exactly the same and you hit it exactly head on, well, if m1 equals m2, this is 0, right? So that means that this one's going to hit this ball, this one's going to stop, and then this one is just going to fly off. If this is more massive than this, then this will be positive. So this will, all right, and of course this will be positive, so this will fly off that way, and this will fly off that way. Okay. Now the next two I'm going to do in gory detail because you're going to need to know how to do this for a lab. So let's do it carefully. All right, what we want to do is we want to say M1 is tons less than M2, right? So just imagine that this is a sphere made out of plastic, and this is a sphere made out of tungsten, or something like that, okay? So this is much, 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 much larger than this, okay? Well, let's do it. So here you go. This is math. So V1 final equals M1 minus M2 all over M1 plus M2 times V1 initial, or V initial 1, whatever, who cares. All right, so here's the math trick. So when you have a situation like this, where this one is really, really big, divide top and bottom by the mass that's really, really large. So M2, 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 M2. And that's perfectly legal, right? That's just algebra. You know, if you do something to the top, you do it to the bottom. So that's perfectly legal. Okay, now let's simplify it. M1 is tons less than M2. So what's M1 divided by M2? Well, it's basically 0. Okay, M2 over M2 is 1. Okay, M1 over M2 again. M1 is tons less than M2, or you can just say M2 is tons greater than M1. So this is 0. And that's 1 again. All right. 0 minus 1 is negative 1. 0 plus 1 is 1. Negative 1 over positive 1 is negative 1. Ta-da! So V1 final equals minus V1 initial. So what does that mean? It means that if this is super light and this is super massive, that it has some initial velocity. It's just going to hit this guy and just turn around and go back with the same speed. The same speed. All right, let's do V2 final. So V2 final equals 2M1, skip a space, over M1 plus M2 V1 initial. Okay, again, divide by the large one. So divide by M2, M2, M2. Now, we don't have to waste our time on this one. M1 over M2 is 0, right? So I don't care about that. This is going to be 0 because M1 is tons less than M2. Well, 0 times anything is 0. So it's 0. So V2 final is 0. So again, this is really light, this is really heavy. This thing smashes this thing doesn't even move. This thing just rebounds with the same speed. All right, and I'm not going to do it, I'll have you do it.